Hello everyone, welcome to tutorial 5 for Introduction to Chemical Engineering Design. So we will start off with question 1. You have 10 pounds of CO2 in a 20 feet cube of fire extinguisher tank at 30 degrees Celsius. Assuming that the ideal gas law holds, what will be the pressure gauge on the tank read in a test to see if the extinguisher is full? So basically we have two conditions here. One is the condition inside the extinguisher tank, and another one is that the CO2 is at standard condition. So we have two approaches to this problem. The first one, we first identify the standard condition, which we term it as 1. So at standard condition, our pressure will always be 1 atm and temperature will be 0 degrees Celsius. We shall convert it to 14.7 psia and 273 Kelvin. Now, based on the ideal gas law, we know that the volume of 1 pound mole of an ideal gas at standard conditions of 0 degrees Celsius or 0 degree Fahrenheit and at 1 atm is 359 feet cube. So what does this mean is that volume of 1 pound mole of an ideal gas. That means this sentence here means the volume over the number of moles per pound mole, in which we write it as V with a cap. Okay, I'll call it V cap, which is 359 feet cube per pound mole. So we already have this, we can determine our volume. We know that we were given 10 pound mole of CO2. So to convert it to volume, we multiply V cap with N, the number of moles. But we are given here the mass of CO2. So we have to convert it to the number of moles by dividing with its molar weight. Okay, this one is the molar weight. Now the conditions inside the tank is the pressure is what we want to find, and we were given that the temperature inside the tank is 30 degrees Celsius and the volume is 20 feet cube. So to solve for P2, we know that since PV equals to nRT and both are the same amount of gas, we know that nR should equal to PV over T, in which N multiplied by R is the same in both of the condition. Both holds the ideal gas law and both has the same number of moles of CO2. So we can equate the equation so that it looks like this. P1 V1 over T1 equals to P2 V2 over T2. Rearrange the equation so that we have P2 on the left hand side, and then we substitute the values that we have found just now into the equation. So this is your P1, this is your V1, this part here is your V1, and divided by, so 1 over 20 feet cube, this is your V2, and T2 and T1. So overall we found that P2 is equals to 66.6 psia. But this P2 here is in absolute, okay? But the question wants us to find the P gauge. So the P gauge formula is whereby you take your P absolute and minus your atmospheric pressure, P atm. With that, we can find that our P gauge is 66.6 psia minus 14.7 psia, which gives us 51.9 psi. Now approach 2, we use the ideal gas law formula, which is PV equals to nRT, and just substitute N, the number of moles over here is the mass divided by the molar weight of CO2 multiplied by R, the temperature, and the volume. So substitute everything in. we should get 66.6 psia. So same thing, find the gauge pressure by using the absolute pressure minus the atmospheric pressure. Okay. Question 2. You are asked to design a steel tank in which CO2 will be stored at 290 Kelvin. The tank is 10.4 meter cube in volume and you want to store 460 kg of CO2 in it. What pressure will the CO2 exert? Compare the pressure calculated by Redlich-Kwong equation against Swove-Redlich-Kwong equation. Is there a significant difference in the predictions of pressure between the equations? So we need to use two approach here. One is Redlich-Kwong and another one is Swove-Redlich-Kwong equation. So Redlich-Kwong equation is like that, whereby A and B is given by this equation. This one is fixed, yeah? And we were given that we know that R is a constant, an ideal gas law constant, 8.314. Okay, then the temperature is 290 Kelvin as stated in the question. Volume is 10.4 meter cubes, and the mass of CO2 M is 460 kg. So first we convert CO2 to the number of moles by dividing by its molecular weight, which we get 10.455 kilomoles. Next, we can calculate V cap by taking the volume dividing by the number of moles. Okay, the volume was 10.4 meter cube. Divide by the number of moles is what we found here, which we get 0.995. So how are we going to find TC and PC? Very simple. We use the table here. So you have a few information. So since this one is carbon dioxide, we look at the section with carbon dioxide and we notice that the critical temperature TC is 304.2 Kelvin. Okay, Kelvin. How do we know it's Kelvin? This one is stated here. The K here stands for the unit. And the critical pressure here is given in bar. Okay, so the critical pressure is 73.83 bar. Convert it to kilopascal by multiply it with 100. That's the conversion factor. And we get 7,385 kilopascal as our critical pressure. So basically we have everything already and substitute. Okay, let me use a pointer. So substitute your R, which is a fixed value, fixed constant, and substitute your TC that we have found. Substitute PC, and we should get our A value here. Do the same for B. Substitute your TC, R, and PC, and we get B. Now we have R, we have T, we have V cap over here. We have B as well already. And we have A, which is this. Substitute all the values in as so to find that our pressure here is 2.126 times 10 to the power of 3 kilopascal. For the Swove-Redlich-Kwong equation, the only difference is this part here. It changes from A divided by T to the power of 0.5 to A, another type of A. The equation for A is different, multiplied by lambda. So B here, the value of B here is the same, is still the same formula with the Redlich-Kwong one. So A prime here, the only difference is the TC here. For RK equation, the TC is to the power of 2.5, but this one is to the power of 2. So please take note and be careful with your calculations. Lambda is given by this equation, and we have a k here that we can calculate using this formula. Now notice we have a omega here, okay? So how do we get omega? We can get this from the table. Oops. We can get this from the table as well. Omega is here, 0.224. 0.224. Now substitute your omega in to find your k, and then put your k back in to find your lambda. So this one we are doing it in reverse. So your k should get 0.843, and your lambda, substitute your k into your lambda here, should get 1.040. Substitute this one in to find a prime, and b we have already found. There's no changes, okay? But notice that a prime, the value for a prime is much different compared with the reddish Kwong's one. Now, to determine the pressure, we substitute all the values that we have found in here into the equation, the Swerve Reddish Kwong equation, and we get it that the pressure is equal to 2.111 times 10 to the power of 3 kilopascal. So basically, there's not much of difference between them, slightly different. Okay. Moving on to question 3. A 5-liter tank of H2 hydrogen is left out overnight in Antarctica. You are asked to determine how many gram moles of H2 are in the tank. The pressure gauge reads 39 atm gauge, and the temperature is negative 50 degrees Celsius. How many gram moles of H2 are there in the tank? So this one we should use the van der Waals and Redlich-Kwong equations of state to solve this problem. The required coefficients are as follow. So unlike question 2, we have to determine A and B using the formula. We are now given the coefficients over here in this question, so we don't have to do the calculations. So let's write down the parameters, or the information that we are given with. We have V is equal to 5 liter, T is equals to negative 50 degrees Celsius, and if we convert it to Kelvin, we add it with 273, we get 223 Kelvin. So the question gave us P gauge is 39 atm. But remember, whatever the P that we calculate from these equations are in absolute. Okay, so we have to find the P absolute by taking P gauge plus P atmospheric, the atmospheric pressure, in which our P absolute is 40 atm. So later on, when we substitute the pressure in, we will take the P absolute to substitute as the P. R 0.08206. So the R over here in this question is different from the previous questions because we are using a different unit. So how do you determine which R to use, which unit to use? That one is based on your problem, the question. If the problem uses Kelvin, ATM, and gram mole, then you use this gas constant. Next, to find the number of moles of hydrogen in the tank, we can solve it using N is equal to V over V cap, right? So to find N, which is our final objective, we need to solve for volume here first, using either van der Waals or Redlich-Kwong equation. So this is your van der Waals equation. So the first thing here, you notice that this one is a non-linear equation. So then we have to expand this equation first, and we get this. So this one can be cancelled. This one can be cancelled. Alright. And then, although we have expanded, it is in, there's two layers, which means you have a numerator and a denominator. So what we have to do now is linearize the equation by multiplying it with v cap square. We always multiply it with the largest, the denominator with the largest power with it, okay? So after multiplying it, we get a linearized form of the equation, yeah? And rearrange the equation. So you see this one is v cap square and v cap square. So we put these, the ones with the same power or root together, and we get p v cap cube minus this and this. Now if you notice that this is a cubic equation, you have a cube, cubic v to the power of 2, v, and you have a constant. So this kind of equation is a cubic constant. We substitute the values in, we substitute p here, we substitute pb and calculate for this value here, substitute a and substitute the multiplication of a and b here. Then we can use the scientific calculator to solve for your cubic equation to find v cap, which gives us 484.07 cm cube per gram mole. Then we can determine the number of moles by taking the volume, this is the volume, divided by V cap, okay? And we get 10.33 gram mole of hydrogen. Next, we use the Redlich-Kwong approach. So similarly, we expand the equation first. We always expand the equation first. So this side here, multiply with this side, and this side here, we multiply it with a. So we get this. And then the bottom, the denominator, we multiply both the denominator together. Now overall, we have an equation that is, or that has a same denominator. Rearrange the equations and expand it further, you should get this equation. Okay, it's very long, I'm not going to pronounce. And then, after you get this equation, move the bottom, the denominator, over to the left-hand side. Alright, and you should get an equation like this. So see, you have a v cap cube, you have a v cap square, v cap, and you have constants. Rearrange the equation so that it becomes a cubic equation format, as so, and similarly substitute the known values of p here, and use your scientific calculator to solve for your cubic equation to find v cap. Similarly, you get your v cap to be 475.97. The value compared to van der Waals is slightly lower. Alright, so it's not much difference, but it's slightly lower. And then look for your number of moles by taking the volume divided by the v cap, which gives you 10.5 gram mole. Question 4. A mixture of 75% hydrogen and 25% nitrogen in molar basis is contained in a tank at 800 atm and negative 70%, negative 70 degrees Celsius. Estimate the specific volume. Okay, so the specific volume is the V cap of the mixture in liter per mole using K's rule. So we are given that hydrogen is 75%. We write it in terms of fraction is 0.75, and the remaining is nitrogen, which consists of 0.25. The pressure is 800 atm and the temperature is negative 70 degrees Celsius, which also equals to 203 Kelvin. And we need to find V cap, the specific volume. We can determine the V cap from PV equals to ZRT. Okay, but to find the Zm, we need to determine the critical pressure for the mixture of the gas mixture, because we have hydrogen and we have nitrogen inside here. And then we also need to identify the critical temperature of the mixture. So this is the formula to determine your critical pressure and your critical temperature of your mixture. Basically, you take the fraction, okay, the mole fraction multiplied by the critical pressure of that specific compound. For example, if you have H2O here, then you put H2O, the fraction of H2O in the mixture, multiply by the pressure of the critical pressure of H2O plus the other remaining components in the mixture. The same method is used for the critical temperature of the mixture. So we need Tc, which is the critical temperature and critical pressure of hydrogen and nitrogen, which we can determine from the table over here. So H2, the critical temperature is, hydrogen is 33.19. Okay, I'm writing it as 33 Kelvin. And the critical pressure is by taking, okay, over here is bar. I've converted it to ATM. So this one is 13.13 bar, which also equals to 12.8 ATM. Yeah. Now you see here I have a formula over here. So why should I do this? Now, if the gas here is either hydrogen or helium, we need to determine the adjusted critical constant from this empirical formula. Basically, the critical temperature and the critical pressure, we add it with the number 8. Okay, this is the adjusted critical constant. That's why we have an A here. A stands for adjusted. So this one we also plus it with 8 ATM, which gives us 20.8 ATM. So this equation here is known as Newton's correction. And it only applies to hydrogen and helium, yeah? So nitrogen over here, we don't have to do that. The critical temperature is directly, we can obtain from the table, 126.2 Kelvin. And the pressure, critical pressure is 34, which is about 33.5 ATM. So by using the formula in the previous slide, we can determine the critical pressure of the mixture and the critical temperature of the mixture. So why the fraction of hydrogen is 0.75, the critical pressure of hydrogen is over here 20.8 atm, the fraction of nitrogen is 0.25, and the critical pressure of nitrogen, as we have found, is 33.5 atm, which gives us 24 atm. Then we have our temperature, same thing, 0.75 multiplied by 41 Kelvin plus 0.25 multiplied by 126.2 Kelvin, giving us 62.3 Kelvin. So why do we need the critical temperature and the critical pressure of the mixture? That is because we need to determine Z. Okay. To determine Z, we can use this generalized compressibility chart, but we will need the reduced parameter, which is PR, and over here you can see, okay, can you see? TR. So PR and TR is required. So how do you calculate for TR? We take T divide by the critical temperature of the mixture. Even if this question is not a mixture, you can also determine TR by using T divided by the critical temperature. Just that this one, the critical temperature here, we replace it with the critical temperature of the mixture, because each mixture has a different critical temperature. So we have to take note of this. Same thing goes for PR, the reduced pressure. We take P divided by the critical pressure of the mixture. Okay, so TR over here, after we calculated it, is 3.26, and the PR, the reduced pressure, is 33.33. Now, how do we determine the Z with TR and PR value? So PR is on the x-axis here. You see you have 0, 5, 10, 15, 20, and so PR is 33.3. So we draw a line, a vertical line at the point of 33.3, which is about here. Next, we have to draw a line for PR that intersects at, sorry, TR that intersects at 3.26. So how do we look at TR? TR, the line for TR is this thick black line that goes along a bit of a slope like that. So we know that TR is 3.26, which is about, you see, this one, the TR here is 3, the TR here is 3.5. So this, our TR should fall in between here, which is about here. Okay, my line isn't that accurate, but yeah, you can do a better one when you're doing it at home. So this intersection point, we will read our Z, our compressibility factor Z, from here, the y-axis. So what we have to do is, at the intersection point, draw a horizontal line across to the axis on the left and read from the chart. So this one is 1 to 2, so this is about 1.9. So our Z is 1.9. Substitute all your values into the equation, PV equals to ZRT. So because we want to find V cap, the specific volume, which is Z is 1.9, R is 0.08206, multiplied by temperature is 203 Kelvin, divided by the pressure, which is 800 atmospheric pressure, and we get 0.039 liters per gram mole. So that's all for tutorial 5. Thank you.